In this presentation, we're going to talk about looking at what happens when you put a resistor in a circuit with an AC source, and also what happens when you put an inductor in a circuit with an AC source. And different things happen based on the type of component that's actually in the circuit. So we start with the easiest case. So if you have a purely resistive circuit, then Ohm's law is satisfied and the current and the voltage are in phase with one another. So basically we know that, that V equals IR, and so there's this direct relationship between voltage and current. So as the voltage goes up, the current also goes up. And so we can use that to see the fact that they're going to be in phase with one another, right? So the voltage across the resistor and the current through that resistor are always going to be a maximum at the same time and a minimum at the same time, just based on Ohm's law. V equals IR. R is just a measure of how much that component resists the flow of electricity in the circuit. It doesn't do anything special like an inductor and a capacitor do in a circuit, specifically when we're looking at transients in a circuit. So Ohm's law is going to be satisfied. So if I look at mathematical representation for these, if I assume that the voltage across the resistor varies sinusoidally with time, and we're going to say that it has a phase angle of 0, then the voltage across that resistor has some maximum value or some amplitude. And I can determine the current in that circuit by taking the voltage across that resistor and dividing by the resistance, according to Ohm's law. When I plug in that voltage that's sinusoidal varying, I can divide then by the resistance. I can factor out the amplitude of that voltage, that maximum value, divide by the resistance, and I can call that voltage over the resistance some maximum current value. And now I have something that represents sinusoidal varying current, where the current is in phase with the voltage supply. They both have the same phase angle. And I can determine what that maximum value is for the current or the amplitude of that current source by just taking the amplitude of the voltage across the resistor and divided by the resistance. Or we can write it in this way. So there's different ways that we're writing things here, and we have to be careful. So we're using lowercase variables to represent sinusoidal varying functions, right? So this is the voltage across the resistor. It's lowercase v, it's sinusoidal. Here, this is also lowercase I, it's the sinusoidal varying function. When we represent the values with capitals and not in bold, we're just talking about, in this case, the magnitudes, right? So the magnitude or the amplitude of that voltage across the resistor is going to be equal to the amplitude of the current times the resistance because of the fact that they're in phase. The other way we can represent these is in Phasor notation, and we try as best as we can to use bold for Phasor notation. So I could represent this sinusoidal varying voltage across the resistor in Phasor notation as having a voltage that would lie on the 0 axis because there's no phase angle, and the current also has a phase angle of 0, and it would lie on that 0 axis. So these are the Phasor notations, and these are the amplitudes. So basically, Ohm's law is still satisfied if you have just a single resistor in a circuit with a sinusoidal varying supply. Ohm's law is valid, and Ohm's law is going to be valid throughout all of AC circuits, even if you have inductors and capacitors, and eventually we will talk about that. So suppose that I have a purely resistive circuit, and it has a current going through the resistor that is 12 amps times sine omega t minus 18. And the resistance in the circuit is 5 ohms, and we want to determine what is the voltage across that resistor. We can use Ohm's law. The voltage across the resistor is the current times resistance. I'm writing this strictly in terms of sinusoidal varying functions. So this would be the resistance is 5 times the current, which is 12, which gives me 60. And then the sine function is exactly the same as the current, so it would still be sine omega t minus 18. So the current and the voltage across that resistor are in phase with one another. And our picture would look something like this if we were drawing the waveforms. So they're phase shifted to the right with a value of 18. Yes, sorry. I was thinking about the phase shift and whether it should be to the right or to the left, but it's a negative value, so it's phase shifted to the right. Okay, so now what happens if you have an inductor in a circuit and it is purely inductive? You have a purely inductive component. So you have an AC source and you have just a single inductor in the circuit. It turns out that there's a phase lag between the voltage and the current, and it turns out that the current lags the voltage by 90 degrees. So if you think about how an inductor works, and if you think about a transient circuit with a switch, if you had a constant voltage supply, and then you had a switch and you had an inductor in the switch, if you had an inductor in the circuit and then the switch was opened, when you first close that switch, the inductor develops a voltage to oppose the flow of current. So there was no current flowing initially. The inductor develops a voltage to oppose that current, and then eventually over time that voltage goes down and the current through the inductor just reaches a steady state value. So if you think about how an inductor behaves in a transient circuit with DC, it sort of makes sense here that the current would lag behind the voltage. So when current tries to flow through that inductor, there's a voltage that's induced across that inductor that opposes that change in the current, and so that voltage comes first, and then the current lags behind it afterwards. Now we can see this with the formulas as well. So we can write the voltage across an inductor as the inductance times the rate of change of the current through that inductor. So remember that that comes from the magnetic field changing and a flux, and there's voltage induced because of that. So if we look at the current that we're given that has some amplitude times sine omega t, we can take the derivative of that sine function, and the amplitude doesn't change with respect to time, but sine does. And when I take the derivative of sine, I get a cosine. But then I also have to take the derivative of what's inside, and the derivative of omega t brings out another omega. So I can now bring together the angular frequency, the inductance, and this current, this amplitude of the current, and I am going to define that, everything that's in front of the cosine, as the amplitude of this voltage. So I'm defining those quantities in front as the amplitude, and I've separated it out so that it looks like Ohm's law of V equals IR. So this piece right here must have the same units as resistance, this angular frequency times the inductance, and it turns out it does, and there's a reason for that, and we're going to talk about that. So pulling those terms out and replacing them by the amplitude of that voltage supply, I now have a voltage supply across that resistor that's varying sinusoidally, but unfortunately it's varying with respect to cosine instead of sine, so I can use a trig identity, and I know that cosine omega t is the same thing as sine omega t plus 90 degrees. So we started off by saying that the current is going to lag behind the voltage by 90 degrees, and we end up using our expression for the voltage across the inductor and how it's related to the current, getting a voltage that does indeed lead ahead by 90 degrees that current supply. So if we were to draw a picture of these, we have our current that is varying sinusoidally, and then we have our voltage across the inductor, which is also varying sinusoidally, but has a phase angle of 90 degrees. So it's shifted to the left by 90, which means that at time t equal to 0, the voltage is a maximum when the current is a minimum. And we can also see that over here in terms of our phasor notation, that the voltage across an inductor leads the current through the inductor by a factor of 90 degrees. And that's always going to be the case. So for inductors, the current is always going to lead, I'm saying that backwards. For an inductor, the voltage across the inductor is always going to lead the current through the inductor by a factor of 90 degrees. Or you can say the current lags by 90. A lot of times in terms of notation, we like to use the voltage as the reference. And if we were to take that previous picture and shift everything, we could draw the picture so that the voltage across the inductor is the term that is has a phase angle of 0, and then the inductor would have a phase angle of negative 90 degrees, so that you can see that the voltage leads the current by 90 degrees. So there's really not a big difference between this picture and this picture. So the only difference is we've taken these phasors and basically just shifted them by 90 degrees. And it doesn't really matter where you start. So traditionally, though, the voltage is the reference. And so it's easier to see here that the voltage is leading by 90 degrees. Maybe, I don't know, that one is easier than the other. And of course, leading means it reaches its maximum first, right? So here's the voltage reaching its maximum first, and then there's the current. If we compare, and I sort of alluded to this before, if we compare the voltage across the amplitude of the voltage across the inductor to the amplitude of the current, we had this expression where I basically pulled out the terms that were in front of that cosine. That was the angular frequency, the inductance, and then the current. And I said, I'm just going to call that the voltage because remember, go back, right? This term right here was the voltage. And I knew that the voltage across the inductor had to have some amplitude, so I just took all those terms that were out in front after I took the derivative, and I just said that has to be the voltage. So I have this expression up here for the voltage, and I realize that it looks very similar to Ohm's law. V equals IR. So the term that's in parentheses here has to have the same units as resistance, because if V equals IR and R has resistance of ohms, then the angular frequency times the inductance has to also have units of ohms. And if you think about what resistance in a circuit represents, the resistance in a circuit is representing how much that component resists the flow of electricity through the device. And so in the case of inductors, we have this thing called inductive reactance. And we write it as an X and with a subscript L. And it is the ratio of the voltage maximum, the amplitude, I guess, of the voltage across the inductor divided by the current. And it's just this term that's out front here, the angular frequency times the inductance. And it's going to represent a measure of how much that particular component, along with the AC source that's running through it, opposes the current in the circuit. So the larger the inductive reactance, so here's my inductive reactance, the larger that this value is, the more resistance to the flow of electricity there is in that particular component. And the inductive reactance depends on not only the actual inductance of the inductor, but the frequency at which that source is oscillating. So omega is the angular frequency in radians per second. L is the inductance in Henry. And as long as you have the angular frequency in radians per second and the inductance in Henry, when you multiply those together, you would get units of ohms, which is the same units that we have for resistance. So this is really sort of the equivalent of Ohm's law for inductors, keeping in mind that these are magnitudes only. They have nothing, it's not telling us anything right now about phase shift or about how these are varying sinusoidally. So we have this summary of Ohm's law for pure inductance. So we can say that V equals I instead of R. We have reactance, inductive reactance. We could rewrite this as the current is the voltage over the reactance instead of resistance. Or, for that matter, we could solve for the reactance as the voltage over the current. So basically, the easiest thing is just to remember the first one, which looks very similar to Ohm's law, except instead of resistance, we have this reactance, and the reactance depends on the inductance in the circuit and the angular frequency at which the circuit is oscillating. So suppose that we knew the current through an inductor, and the inductor has an inductance value of 0.01 Henry, and that the current that's flowing through that inductor is 20 amps sine omega t minus 50 degrees, so it has some phase shift to start with. And in this particular case, we actually have to know the frequency at which this source or this current is oscillating, because the reactance in the circuit, the amount the inductor resists the flow of electricity, depends on how the source is actually vibrating. What is that frequency? And we'll talk a little bit more about that in a second. We want to determine the voltage across the inductor. We know that in an inductor, the voltage leads the current by 90 degrees. So that means that we can write the voltage across the inductor as having some amplitude times sine omega t minus 50. That's what's inside here for the current, but then we have to add 90 degrees to it. We can figure out what the amplitude of the voltage is by taking the amplitude of the current and multiplying by the inductance times the angular frequency. This, in parentheses, is the reactance. I know that the angular frequency is just 2 pi times the regular frequency, and our regular frequency is 60 hertz. So I can plug my numbers in. 2 pi times 60 hertz times the inductance of 0.01 Henry times the amplitude of the current, which is 20 amps, and I get an amplitude of 75.4 volts. So I can plug this value in for the amplitude of my voltage supply, and I can take 90, which is positive, plus a negative 50, and I get 40 degrees. And so my voltage across the inductor would be 75.4 sine omega t plus 40 degrees, which is leading the current by 90 degrees. If I were to draw a picture of this, here is my waveform picture. So my voltage is in red, 75.4. It is shifted to the left by 40 degrees because it's a positive 40 degrees. My current is shifted to the right by 50 degrees, and it has an amplitude of 20. If I wanted to represent these in phasor notation, remember that we use effective values or RMS values in phasor notation. So I would need to figure out the effective value for the voltage by taking 75.4 divided by the square root of 2, get 53.5, and I would do the same thing for the current. 20 over the square root of 2 is 14.1. And then I could represent these in phasor notation so that the voltage across the inductor, the phasor would be at an angle of 40 degrees, and the value of the length would be 53.3, and then the current would be at minus 50 in phasor notation with the amplitude, not the amplitude, but the effective value of 14.1 amps. So this gives us a visual representation of the example that we just looked at. So I sort of alluded to the fact that this reactance, this inductive reactance, acts like resistance, and it really does. So the larger the inductive reactance is in a circuit, the more that inductor is resisting the flow of electricity in the circuit. Now let's think about what the inductive reactance depends on. It depends on the angular frequency, so how quickly is the voltage or the current in the circuit oscillating. So a large angular frequency means that this is oscillating very quickly. The current is changing very, very quickly. And an angular frequency that's smaller means that the current is changing very slowly. And of course, the inductance is just measuring how much that inductor can resist the magnetic field changing, right? So a large inductance means that there could be a large flux through the circuit. So what does this mean? So this picture that I have here represents the reactance, the inductive reactance versus the frequency, and then I have different values for the inductance. So one of the things that we notice is that that the inductive reactance is directly proportional to the frequency. So the more that the circuit, the more that the source, the current source or the voltage source are oscillating in time, the greater the resistance to that flow or to that, the greater the resistance is by that inductor to the current that's flowing through that circuit. So a lot of oscillation means that that inductor is really resisting the flow of electricity. And if you think about an inductor, remember inductors, I put in parentheses, don't like change. And so they will do everything in their power to resist a lot of change. And so if you have a large frequency, that means your source is changing very quickly and very often, and an inductor is going to resist that. So there's going to be more resistance that way. The other thing that's true is that for a set frequency, let's look at 200, right? So a set frequency, depending on the inductance, you'll have a different amount of reactance. So the larger the inductance value, the bigger the resistance is going to be. So here I'm at 200, right? And I have this inductor here is resisting and has a reactance of 3,000, but this other inductor, if I go up and I follow it, it has a reactance that is much larger. So L2 in this picture has a larger inductance than L1, and it's going to create a larger resistance to the flow of electricity in the circuit. So think about reactance similar to what you would think about resistance. It's measuring the resistance to change or the resistance to the flow of electricity due to that particular component.